Hello, can you hear me well? Yeah, so my name is Ilya Katsov. I'm VP of Technology at Grid Dynamics, and in this talk I'm going to present some best practices and also talk about some challenges associated with building ML platforms for smart manufacturing and IoT. And most of this presentation is actually based on our experience with Grid Dynamics, working with manufacturing, pharmaceutical, semiconductor companies, both in the United States and in Europe, on different types of innovative programs related to data science, advanced analytics, and building edge solutions, IoT solutions, and so on. And I would like to start with a brief overview of typical use cases that we usually want to solve using AI and ML platforms in smart manufacturing or pharmaceutical domains. And because these use cases, they generally dictate what kind of capabilities this platform needs to provide and how we approach building this platform. So first, very typical group of use cases is, of course, quality control automation. So these use cases, there are different ways how we can go about visual quality control. In some cases, visual quality control is done based on numerical metrics that are collected from sensors or from measurement devices or from connected devices. We basically can do analysis of these measurements and detect defective parts or something like that, and then operationalize this solution by removing these parts and so on. Another typical category of use cases is doing visual quality control, which requires to connect with industrial cameras, and then based on their videos or images from industrial cameras, we do anomaly detection in these images or compare these images with some references and detect anomalies this way. And for this, this is of course very important scenarios because costs associated with quality control are very significant. In many cases, it can be like 10 to 20% of company revenue for certain industries. And implementation of these use cases generally requires requirements and provides several features from the platform side. So first one is that actually data preparation and data labeling is typically very expensive in many industries because data labeling for this type of use cases can be done in many cases only by domain experts. For example, if we are talking about some, like semiconductor industry or production of like continuous production scenarios, then it's very challenging actually to label images properly. It can be done only by domain expert. You cannot just hire any person to do this job. It requires a lot of expertise, a lot of experience in a particular industry. So the bandwidth is generally like limited. There are only like so many images you can process, and data preparation is generally very expensive. So, and this needs to be addressed in the platform by providing typically good data labeling tools that are typically, in many cases, they are domain specific. They are developed custom for specific scenarios. Then, of course, we need low inference latency because typically we deal with like hundreds or even thousands of measurements or like items that needs to be analyzed every second, and it requires to do inference with very low latency and with very high throughput at the same time. So, which also, of course, influences the design of the platform. And finally, these solutions, they typically need to be integrated with multiple production lines, with multiple facilities, which implies that we need to support distributed deployment capabilities in this platform and provide good level of deployment automation. So this is very important for operationalization as well. The second group of use cases that are also very common are related to operations control. Basically, in operations control, what we are trying to do, we are trying to adjust or manage parameters of equipment or physical processes in order to do certain type of optimization. For example, we can it's often used to optimize the quality of the outputs. For example, like the simple example from the food production domain is it can be some commercial oven that bakes, for example, bread, and you need to manage parameters, like temperature and, like speed of the belt and other parameters in order to avoid, producing low quality results like underbaked or overbaked. bread. And traditionally, it can be done using some like manual adjustments, regular adjustments, but it usually results in a relatively like broad range of outcomes. And this type of solutions, they aim to like reduce the variance of in the quality, reduce the variance in parameters. Basically, we build like a complete feedback loop that make adjustments of these production parameters based on, for example, cameras that take pictures of the output product. And this is, of course, very simplistic example. It can be much more sophisticated than that, but typically this is the idea. And for implementing this type of solutions, there are several characteristic features in this type of problems. First, it's very common to chain multiple different models. For example, it can be computer vision model that estimates certain parameters based on pictures of the output, and then this model can be chained with some simulation models that does some sort of optimization, and then based on this optimization we determine optimal parameters that correspond to the current situation, and then we activate these parameters and the process repeats. And also, in this type of use cases, it's also very important to have good observability into the inference process, obviously, because we making like real changes, automatic changes in the production processes, and we need to have good insight into, good alerting capabilities and good insight into how models performs over time and all safety checks and so on. Finally, the third category of use cases I would like to mention are use cases related to predictive maintenance. This is, of course, very important because different costs associated with inefficient maintenance, like reactive maintenance or preventive maintenance, they can be like very significant and higher than optimal approach that we can achieve using predictive maintenance. And in this type of scenarios, we generally need to collect different metrics from different parts of equipment or vehicles, aggregate them in the central platform, usually train the model based on that captures typical patterns, typical behavior of this equipment. And then the models needs to be deployed either on edge or it can be centralized services. And for this type of scenarios, again, there are several characteristic features, like in my experience, like data preparation and building a valid model is extremely important in this type of scenarios because it's very easy to build, for example, anomaly detection model that actually does not match the semantic of the physical process, and it will produce detection results that are not really like operationalizable or invalid. Then the second feature is that in this type of scenarios, actually, it's very common to deal with high-dimensional input data. It can be like literally thousands of metrics per machine, and detecting of anomalies in this type of settings is very challenging from a statistical standpoint. It generally requires to use very specialized machine learning techniques to accommodate for that and to be able to reliably detect anomalies if it is possible at all in this type of data. And finally, it's also important to provide a sort of a prescriptive guidance in many cases to operators, because it's not just enough, for example, to flag anomalies in certain cases. It requires to provide some guidance on root cause analysis. It also, in many cases, it's important to provide some insight into how, let's say, one particular facility operates compared to other facility and what are the potential areas of improvement and so on. And it also requires to build like specialized logic and specialized models for that. So how do we summarize, like how do we incorporate these different requirements, these different features into the platform design? So typically what people are doing, they're approaching it in the following way. So let's say that we have this physical process and we have some sensors or cameras that are attached to this process, and we have some interfaces that can control the parameters of this process, like PLCs. The first problem that we need to solve, of course, is connectivity. We need to I'm just talking in this slide at a conceptual level what's the logical architecture of a platform that enables these different use cases. First problem is that we need to solve connectivity, and we need to provide ability to collect metrics or images and send them to some centralized facility for the analysis. And this requires, of course, integration with the hardware, but then we also typically need to deploy data collection management services on edge so that we can manage the collection process, and then the data is streamed typically through some central location. It can be public cloud or private cloud. There are a number of ETL processes associated with that. Finally, data lands into storage, and then typically, we would need data labeling, and as I mentioned, in many cases, we need to build custom data labeling tools in order to do domain-specific labeling in an efficient way so that labeling experts can work productively. And then we, of course, need model development workbench to do actual analysis of the data and build these different types of models that we talked about. Then these models needs to be basically packaged into artifacts, and these artifacts can be deployed as centralized services, or they can be deployed on edge in many cases to achieve low latency and high throughput of inference. So generally, we can build two types of inference services either on edge or in the cloud location, and these services that needs to be connected to our control interfaces. And finally, the last part that I want to mention here is observability. We basically need to collect metrics about how models are performing, what's the outcomes, what's the drifts, and so on. And then this information goes through, again, these collection services and lands in some observability tools for model monitoring, for process monitoring, and so on. So this is how the typical basic layout looks like from a conceptual perspective. Then this layout, of course, can be mapped to some technical architecture. There are many different ways of how it can be done. This is just an illustrative example, how it can be, one particular case of how it was mapped to AWS-based architecture. I will not go into these details. Of course, this is just, an illustration. There are many, many different ways of how specifically it can be implemented and what products can be used. But in the rest of this presentation, actually would like to talk about like edge cases, some challenging scenarios that are beyond this basic platform. So let's say that we built this basic ML platform that I talked about with these standard capabilities like edge deployment automation, data collection, labeling, model development, continuous integration, inference, observability. In reality, of course, the adoption of this type of platform is much more complex than what we talked about. And I want to talk about several typical issues or pitfalls that manufacturing companies need to solve in their journeys. So first one is that this platform typically need to be integrated with multiple suppliers or multiple OEMs or that can locate in multiple countries, that can run multiple facilities and so on. And these different facilities, they can provide different level of access. So it's not always possible to deploy, for example, something on edge. It can be other connectivity challenges because of various reasons, because of business reasons, because of technical reasons. And this needs to be addressed. And also it can be some specialized types of analytics like facility performance analytics, comparing different facilities to each other, and supplier compliance control that needs to be implemented in this type of scenarios. So this is one interesting example. Then the second aspect that I'm going to talk about is building specialized, using specialized cloud services. Because what we talked, scenarios that we talked about, like visual quality control or anomaly detection, they generally, they not necessarily require to build all these models from scratch. There are like a number of out-of-the-box components and services that are available, and integrating the services, it actually, from one hand, it of course, on the one hand, it of course facilitates the process, but it also associated with like certain challenges that might need to be overcome using some techniques. And finally, the third item is the efficiency of development teams, because this basic platform that we talked about it generally enables the development of these solutions, but it's not like it's essentially a baseline that can be used to build even more efficient services that improve the productivity of development teams. And I will talk about that. And to illustrate these three challenges, these three aspects, I'm going to show three real-world case studies based on projects that we did. The first one is a project that was done for a large electronics manufacturer. The goal was to build a quality control solution based on metrics. So basically, it was like a production line with electronic devices, and at different stages of production, different measurements were done, and these metrics were collected. For each measurement that actually could be quite a large number of metrics, like several hundreds of different metrics at the same time. And the goal was to build a solution that essentially detects anomalies in these metrics and gets the defective parts removed. And but the challenge was that this manufacturer, they had multiple like suppliers, OEMs, and they delegated this production to them. So they had basically two types of facilities. The first type was facilities with ability to deploy like on edge and do real-time calls to the cloud. And in that case, it was like relatively straightforward solution. Basically, the metrics were collected from edge and sent to a centralized service. It was associated with some latency, but in their case, it was not that critical. And then scoring models were used to score essentially like propensity to defect, and then some decision-making logic was applied to it, like thresholding to determine defective parts, and then defects were communicated back and like removed from production lines in real time. So this was a solution for factories with direct access. But in order to deal with facilities for which they did not have ability to make these calls directly, we actually had to implement like a totally different solution. And this solution was based on essentially specifications. What they could do in these black box facilities with some of the like Asian OEM suppliers, they could only send them some specifications and thresholds for these measurements. They were not able to do actual scoring in real time, but they could provide some specifications. If these thresholds, if there's certain metrics measurements within certain thresholds, then the part is good, otherwise it is bad. And it required to create a completely different set of models to optimize these detection thresholds, produce the specifications, update the specifications, and then the specifications were sent to actual facilities, and they use their own processes that we actually did not have transparency into to do this defect control and reported back some SLAs. So this is an example of how these connectivity challenges can result in two completely different solutions. Then the second item that I mentioned is integration with specialized services. So this is an example from the food production industry. There are basically like food production lines that produces chocolate cookies in this example, and the goal was to implement visual quality control solution that detects basically like anomalous items. And there are a number of services available for that allow to detect anomalies like in images, but the challenge was that we do not have like images of individual cookies. We have like a conveyor belt, and we basically have a footage like that. And it requires to like create a separate pipeline to essentially do some cleaning of these images, like remove shadows and so on, and detect individual objects. And then this individual object was sent to a standard anomaly detection service. And scores were produced by this service and then used for actual operationalization. And this is again very typical scenario that it's actually very typical to maintain like libraries of these different adapters for pre-processing and post-processing, in addition to standard services that solve some basic tasks such as anomaly detection in individual image patch. And the third example, a third case study that again is from electronics industry is around building services that improve the productivity of the development teams. So the background here is that the electronics manufacturer, they needed to produce many different anomaly detection and other computer vision models for production purposes, and it was not very efficient for them to have like multiple data science teams to do it, kind of manually using just basic tools. And we ended up with creating like a custom service that could be used to solve standard typical problems. For example, clustering of images, classification, and object detection. And the service supported a standard format, basically any person, any analyst or data scientist could go into the service, provide images with certain metadata in case of, for example, classification, object detection. It can be bounding boxes, it can be labels uploaded into the service, train the model, and then get some evaluation results for this model and download the binary artifact or get this artifact deployed in the artifact repository. And it improved the productivity of this team significantly because they could use this service to do basically like standard type of modeling and use more flexible basic tools only to improve, only to solve more custom, more specialized cases. So to summarize, the typical process of building solutions like what I talked about, generally, of course, it requires to do some foundational work in the sense that we need to solve connectivity problem. We need to understand like the lay of the land, what use cases make sense to focus on, establish some visibility into the processes, analytical tools, dashboards, and so on. But then if we are building solutions like visual quality control on, let's say, on a production line, then the work can be separated into several streams. Like typically it makes sense to start prototyping using either synthetic data or some data produced in the lab and have this track separate from building the platform and from hardware integrations. Then in parallel with that, it can be a track related to implementing this platform that requires to select products, including specialized services, implement the like end-to-end automation and implement hardware integrations, and then these three tracks can converge not necessarily into completely automated solution, but into a solution that provides certain level of automation and some operations like model deployment can still be done in like manual mode. And then from that we can go to complete end-to-end automation and close certain automation gaps in this process. Yep. So that's it from me. So this is I hope it was helpful as a kind of overview of some some challenges that can be associated with building this type of platforms and solutions. So thank you.